This video is brought to you by mywayteaching.com.
Dear students, let us see one more problem. If the size of a nucleus in the range of 10 raised to minus 50 to 10 raised to minus 40 is scaled up to the tip of a sharp pin, what roughly is the size of an atom? Assume tip of the pin to be in the range of 10 raised to minus 5 meter to 10 raised to minus 4 meter. Here, the size of a nucleus is in the range of 10 raised to minus 15 meter and 10 raised to minus 14 meter. The tip of a sharp pin is taken to be in the range of 10 raised to minus 5 meter and 10 raised to minus 4 meter. So the tip of a sharp pin is in the range of 10 raised to minus 5 meter to 10 raised to minus 4 meter. This is the range of nucleus, actual range of nucleus. And here it is the range of tip of the pin. Now it is scaled up from 10 raised to minus 15 meter to 10 raised to minus 5. So by this we can say the scaling factor is 10, isn't it? The scaling factor is given by 10. That is, it is scaled up by a factor, that is 10 raised to 10. An atom roughly of size 10 raised to minus 10 meter will be scaled up to a size of 1 meter. Okay, the atom which is having a size of 10 raised to minus 10 meter, since the scaling factor is 10 raised to 10, it is scaled up to 1 meter. Thus, a nucleus in an atom is as small in size as the tip of a sharp pin placed at the center of a sphere of radius about a meter long. Now, let us study the range of lengths. The sizes of the objects we come across in the universe vary over a very wide range. These may vary from the size of order 10 raised to minus 14 meter of the tiny nucleus of an atom to the size of the order of 10 raised to 26 meter of the extent of the observable universe. So it can vary from 10 raised to minus 14, which is the size of the nucleus, to the observable universe size, that is up to 10 raised to 26 meter. So we also use certain special length units for short and large lengths. These you should remember these special units which are used for short as well as long lengths. So one Fermi is given by 10 raised to minus 15 meter. 1 Fermi is given by 10 raised to minus 15 meter. Similarly, 1 angstrom is given by 10 raised to minus 10 meter. And similarly, 1 astronomical unit, 1 AU, that is average distance of the sun from the earth. So that is given by average distance of the sun from the earth is given by 1.496 into 10 raised to 11 meter. Similarly, 1 light year, okay, 1 light year is given by 9.46 into 10 raised to 15 meter. So 1 light year is given by 9.46 into 10 raised to 15 meter. that is the distance that light travels with velocity of 3 into 10 raised to 8 meter per second in 1 year. So these are some of the very important short and large lengths. One more important unit is called as parsec. Okay. So 1 parsec is given by 3.08 into, so 1 parsec is given by 3 into 3.08 into 10 raised to 16 meters. Okay. So this parsec is the distance at which average radius of Earth's orbit subtends an angle of 1 arc second. So the radius of Earth's orbit subtends an angle of 1 arc second. So that distance is called as 1 parsec. Okay. Measurement of mass. What is this mass? Yes, the amount of matter in the substance is called as mass. Okay. Since mass is an internal property of matter, usually it does not depend on external circumstances like temperature, and pressure. So it does not depend on these external parameters. The measurement of mass can be done with the help of a simple balance. You know, right? Simple balance, how it looks. In that, we usually, the gravitational force on a given object is compared with the gravitational force on some standard object. Here, in simple balance, it will be like this. We'll balance it, and at one end we'll tie so here we'll put 1 kg, 2 kg, some standard weight, and here one side we'll put our objects, isn't it? So the gravitational force of this object is compared against the gravitational force of this standard. So remember, the mass playing role in gravitational force is called as gravitational mass. Okay. And hence the mass determined with the help of a simple balance is called as gravitational mass. Okay. It is related to gravitation. So it is called as gravitational mass. The gravitational mass of an object is the same at all places on the earth. The gravitational force on an object of mass m is called as weight of the object. So whenever we say the gravitational force on an object of mass m, if mass of the object is m, and along with that the gravitational force is also added for that mass, and this product is called as weight. Okay, weight of an object. We can say that the weight of a body at any place depends on the value of gravitational acceleration of that place. For example, the weight of a body on earth, okay, the weight of the body on earth is different compared to weight of the body on moon, isn't it? Because there the gravitational constant or the gravitational value in moon will be different, and in earth it is different, isn't it? So it depends on that the gravitational force on the particular place. Or in the entire earth, the gravitational force, it remains constant, that gravity force. So weight also remains constant in the earth. But when we go to moon, again it depends on the gravity of the moon and it changes there. So while dealing with atoms and molecules, the kilogram is an inconvenient unit because we can't measure it using kilogram, isn't it? Yes. Therefore, their mass is measured in atomic mass units. Okay, it is measured in atomic mass unit, that is called as AMU. The 1/12 mass of an unexcited atom of C12, that is carbon 12, is called as 1 AMU. Okay, in that carbon 12, that 1/12 of mass, 1/12 of mass of this carbon 12 is called as 1 AMU. Got this? And the value of this 1 AMU is given by 1.66 into 10 raised to minus 27 kg. It can also be represented as 1 U. In physics, we come across very wide range of masses from 10 raised to minus 30 kg to 10 raised to 55 kg. So the range is really very vast. That is from 10 raised to minus 30 kg to 10 raised to 55 kg. Got this? Yes. Large masses like planets, stars, and even galaxies can be determined from Newton's law of gravitation. For measurement of small masses, we make use of mass spectrograph. Okay, if you want to measure a very small particles like atomic particles or atom, we make use of this mass spectrograph. Okay. And for measuring this large masses, we use Newton's law of gravitation. Okay. So this is all about measurement of mass. Moving to the next part, that is measurement of time. In the early days, time was measured from the length of shadows of objects cast by sunlight, isn't it? Yes. After the invention of the pendulum, there is much development has taken place in the measurement of time. To measure any time interval, we need a clock. You can see in this figure. So, to measure a time interval, we use this clock, isn't it? Yes. In order to meet the need for a better standard for time, atomic clocks have been developed. Okay. Not only these are all normal clocks. Along with this normal clocks, we also have atomic clocks to measure the time more accurately. Okay. Atomic clocks have been developed. For the measurement of small time intervals, camera multi-flash photography are being used. Okay, even to measure even minute time also means very small intervals. We use this camera multi-flash photography, etc. Okay. So in the early days, we were using those, we used to take the reference of shadows to determine the time. Later, we developed the pendulum and then we are using this clock, and now not only clock, we have atomic clocks, and even to measure the minute, what we can say, very small interval, we are using this multi-flash photography, camera, etc. Okay.